I want to consider a linear system that's homogeneous. Homogeneous means that there's no plus extra stuff in T, uh, functions that are constants added on. Everything's in terms of x1 and x2 or more. And I'm going to make my life really easy. I'm going to start with a system that's got constant coefficients. Hang on a second. If x equals x1, x2, what's the set of equations that this looks like? What's my set of equations? Am I alone in the room? What's the set of equations? No, it's not augmented. No, not for a system. It's not minus. It's plus 3x2. And what's that equal to over there? It would be x1 prime. Second equation follows the same setup. 5x1, because it's across the row and down the column. Wait a minute. Before I do anything else, let me think about this. I am going all the way back to Calc 2. What I have here is a slope. The change in x and the change in y, right? So if I were to try and think about this as having an x1, x2 plane, if you picked a point, you could go back and figure out change in x1 and change in x2, right? And if you drew that, that would be a slope. Change in y over change in x. You could make a slope field. And at every point, you could put a little vector that pointed in some direction. I don't know where they are or what they look like, but I know how to make them. In my slopes application, I have a setup for graphing phase planes. I can feed it a system of equations. The system I can choose arbitrarily. So I'm going to change that set of equations right there. I want to start with the top one. Let's get rid of that. I'm going to make it AX plus BY. And then I'll make the bottom one CX plus DY. And then I can go in and tell it what I want the numbers to be. 1x plus 3y, and then 5x, and 3y. There we go. 1, 3, 5, 3. At every single point, it drew an arrow. Yeah. And what I created is based on what I know is going on, based on those coefficients. But now that means if you pick a point, we could do something like Euler's method, couldn't we? If I pick a point, you can tell me what happens as we start moving. And lo and behold, we follow the arrows that are the slope field here. So I don't even have to have a solution yet. And I can say, oh, it's going to look like this. But it turns out that I actually do have a solution for this. We should check this, make sure I'm not blowing smoke up your ass. How do I know that this is right? Plug in what, where? I'm going to treat this like it's really a vector on its own. And I'm going to do the same thing here. And then I'll add those together and I get one big vector. Hey, wait a second. That's my vector x, yes? If that's x, then that's really x1 and x2. Which means I can check it, Cody, by plugging those in here and seeing if they work. Which means I need the derivative of x1. I need the derivative of x2. I claim this does work. What is x1 prime? And if I take, let me go back up here. If I take x1 and add 3x2s, well, that'll be one of those and three of those. That'll give me minus two of these. And it'd be 9 and, sorry, it'd be 3 and then 15. That would give me 18 of those. That's exactly right, isn't it? If I check x2 prime, it'll be the same setup. x2 prime is 2c1 e to the minus 2t plus 30c2 e to the 6t. This is exactly the right set of equations, sorry, the right set of expressions to satisfy that setup. I want to see that it's equal to this, right? So take one of those and add three of those. Doesn't that give me minus two in the first column? And one of these and three of those is going to give me 18 of those, isn't it? So this works. Here's the $64,000 question. Where the hell did this come from? Let me look at that for a minute. C1 e to the something. C2 e to the something. That looks awfully familiar. Where did we see that? Ah, but it came from our second degree thing where we did the quadratic, right? So this is our second order idea, only there are vectors in it instead of just numbers. Well, that means somewhere in this game, I would like to try and say, I'm doing the same thing. I'd like to say, hey, if it worked that way with a quadratic, maybe there's a similar equation I can use based on this matrix. So let me think for a minute about this matrix. And what I'm really trying to figure out is there a vector that when I take that vector and multiply it by this matrix, I end up in the same direction? Let me go back and look at my picture for a second. Here's my picture. If I look carefully, it looks like as I go from top left, I'm going in. If I'm down to the bottom right, I'm going in. If I'm in the bottom left, I'm kind of going out. And if I'm in the top right, I'm going out. It looks like there should be two lines. And everything is kind of zooming in one direction, kind of closing in this way. And then everything's kind of spreading out from some line here and closing in on a line here. But those lines shouldn't move. I should stay in that direction. In linear algebra, we found vectors that when you multiplied them by a matrix, the vector didn't move. It stayed on the line and just got bigger or smaller. And in linear algebra, we gave these vectors a particular name. Okay, people who had linear, what did we call them? Those are my eigenvectors. And those eigenvectors, each one came with a number, an eigenvalue, and that value is how much we stretched. So if I was pointed in this direction and my eigenvalue is 3, I got 3 times bigger. If my eigenvalue is 1/5, I got smaller. If my eigenvalue is negative, I'm still pointed on the same line, I'm just pointed opposite. Okay. Eigenvector is a bastardization of a German word and an English word. It really should be called a characteristic vector or a characteristic value. But eigenvectors stuck around for forever, so we're going to use that one. Back to linear. Given a matrix A, the eigenvalues for A are the numbers lambda, and I apologize, that's been the letter for an eigenvalue for decades. I'm not going to change it on you. So that AV equals lambda V for some non-zero vector V. That vector is called the corresponding eigenvector. Each value gets a vector. Sometimes values get more than one vector. The value could be 0. The vector can't be. Well, wait a minute. If A times V is equal to lambda times V, then AV minus lambda V is 0. Or A minus lambda times the identity, V is 0. And I want my vector to not be 0. I remember from linear algebra, if this equation has non-zero solutions, it means something about the determinants of my vector. And it means that the determinant of A minus lambda I is equal to 0. What the fuck? Okay. How do we compute a determinant again? Right now I'm only dealing with a matrix that's 2 by 2. Aha. AD minus, we did this already, like our Wronskians, right? Because a Wronskian is really a determinant. Okay. So my matrix A was 1, 3, 5, 3. Lambda times the identity is lambda 0, 0, lambda. The lambdas only go down the main diagonal like that. I'm going to subtract. A minus lambda I is 1 minus lambda, 3, 5, 3 minus lambda. By the way, you're also allowed to do lambda I minus A. It doesn't matter which order you do it in. It's going to be 0. It doesn't matter whether you do the a first or the lambda first. Now I do the determinant here. The determinant of a minus lambda I. AD minus BC. Hey, wait a minute. Multiply that out. What kind of an equation do you get? Just like my second order stuff with the m's. R's, we used R. I get a quadratic equation. What are the roots of that quadratic equation? I'm having the weirdest sense of deja vu. Where did I see 6 and -2 already? In the E. Those roots are exactly the powers in our e to the whatever t, just like they were in the quadratic case. Now, those are the eigenvalues. Each value gets a vector. To find the right vector, I need to plug that value back into the equation we were trying to solve and figure out what V works. So I'm going to take one of these numbers. I have to do them both, but I'm going to start with one of them. Which one do you want to start with? Say again? 6. Okay. So if I start with lambda equals 6, I go right here and I put in 6. Now this time I want to set this equal to what? I go back up here. My goal was to set that matrix equal to 0. So I'm going to augment the matrix. I want to set those equations equal to 0. Solve this set of equations. You are welcome to do this not in a matrix if you really want to. You could write negative 5x plus 3y equals 0 and 5x minus 3y equals 0. And what happens? Well, what happens? If you're going to do elimination by addition, what happens when you add these two equations? The bottom row is all zeros, which means there are infinitely many solutions to this. That's good, because that gives me a whole set of vectors that make this work. And they all point in the same direction. They all satisfy the equation minus 5x1 plus 3x2 equals 0. Or you could multiply by -1 And you could say 5x1 minus 3x2 equals 0. Either way, it doesn't matter. Give me a vector, x1, x2, whose numbers make that work. What numbers could you put in other than 0 that would make that work? Anything. Sure, but where do I put what? If I want that to work, if I want this to work, then I know that 5x1 has to be equal to 3x2, right? Or I could say x2 has to be 5/3 of x1. So if I want to make this work, I could say put a 3 here and a 5 there, right? Or I could put a 1 here and a 5/3 there. Or I could put a -2 here. Put that next 2. Wait a minute. If I want to solve this, I get x1 is 3/5 x2. So if I put a -2 here, I put a -6/5 there. They all work, right? Any one of those vectors would work. As a matter of fact, we often put a 1 in one of the spots just to make our lives easy. I don't care which one you put it in. Like that, right? Both of these have a 1 in one of their spots. Any of these would work. But Hayden, to answer your point, why there are infinitely many of them, they all point the same way, right? They're all just longer or shorter or negative versions of the same vector. So they're all on the same line. And that's this line right here. Wait a minute. If I write this line this way, that's y equals 5/3 x. Y equals 5/3 x. It's got a slope bigger than 1. That's one of the directions we're using. So instead of solving for a C1 or a C2, I solve for the direction vector that goes with it. So we use this one with 6, right? If this goes with 6, I should be using one of these vectors times e to the 6t. Now, it really doesn't matter which vector you want to use. We could use this one, or we could use that one, or we could use this. It doesn't matter which one. As a matter of fact, if you go back and look at our original solution, what one did we use? Well, which vector did we use with the e to the 6t? We used 3, 5. You could use any of them. Doesn't matter. If I use this one instead, then my value of C1 would change compared to if I used this one. It works either way. Do this again. Only this time, do it with -2. I got to go back to the I'm sorry, a minus lambda I thing and put in the -2. Scroll back up the page. There's a minus lambda I. Put in -2, and I get 1 minus -2, that's 3. That number didn't change. That number didn't change. 3 minus -2. Hey, there we go. If I simplify this set of equations, I multiply the top row by minus 5/3 and add it together, what happens to the bottom row? It's all zeros. And then I could say, well, let's make our lives easy and divide the top row by 3. I get that. This is called reduced row echelon form in linear algebra. It's on the calculator. More on that in a moment. What's the set of equations that go with this? So x1 is the same as -x2, right? Pick a value, give me a vector. Pick a value for x2. Okay, then I would use -1, 1. Maybe you pick it the other way around. Maybe you choose to use -1, -1, like that, right? You could use 3, -3, or -17, 17. I don't care what number you use. But if we go back and look, this is going to go with the e to the 2t. These are possible vectors. And then I would get something like this. So now I've got my solution, and it's made up of 2 pieces. Each piece has an e to the number t that came from our quadratic equation, and each piece has a vector that goes with that number. And so I get x of t being number times this thing plus number times this thing. Except for the fact that I wrote them in the other order beginning of class, that's the same damn answer, isn't it? It worked. Yes. So for example, if I had used this, it wouldn't be wrong, but whatever value of C2 I'm using here, I'll use the opposite here. If this was 2, then this should be -2. But that'll give me the same result, won't it?
How's that? If that changes, how's that solve?
Ah. So let's suppose in this version, I'll write it in the same color so we can keep the right color with it. Suppose C1 was 2 and C2 was -1, right? Then my equation should look like if I put in 2 there, I get 6 e to the 6t plus, minus e to the -2t, right?
Like the x1, x2 equations always did say?
Yes. Yeah, all I would end up doing is I would have the minus sign on the inside instead of the outside, right?
I thought like x of t would change, so I guess it does.
This version changes, but this version doesn't. I got to finish this out now, though, because they'll bug me if I don't. If I switch to using the other one, then C1 will equal 2, but C2 will equal +1. And then I get x1 is 6 e to the 6t, but minus 1. Okay, so that's minus e to the minus 2t, isn't it? And down here, I'm going to get 10 e to the 6t plus 1 e to the minus 2t. So while this part changed, that changed the value here. Those are the same. Imagine writing the equation for a line. 3x plus 3y equals 0. Isn't that the same as writing 1x plus 1y equals 0? So that's really all I'm doing is I'm changing a scale factor. I solved a quadratic equation. I got two real roots. Those two real roots gave me, now for different C1s and C2s, I'll get different pictures, right? I'll have different initial conditions, X and Y, and I'll be able to draw these curves. They're parametric equations. X in terms of T, X in terms of T, those are parametric equations. A question for you. What happens in either of those as T goes to infinity? Yes, you could use this one or you could use this one.
Second. The e's to the negative becomes 0.
Aha! And that means the e to the 6t is the part that's important, right? So I could really think of this as being x1 is 6 number and x2 is 10 number, right? When t is a large thing, these are the same, which really means I'm doing, hey, you're somewhere out in that direction, aren't you? As t gets bigger and bigger and bigger, we're going to get closer to the line that points in the direction 3, 5. Our curves are asymptotic to this line. They all end up pointing this way. And the further out I go, the closer they'll get to the line whose slope is 5/3. What if I go the other way? As t goes to minus infinity, what happens? Right, the part with the 6t gets really small. And then I could really think of this as being governed by these parts. Which means those are pointing in the direction -1, 1, aren't they? They all go this way. There's the line -1, 1. So my solutions are going from here to here. From here to here. They go away from this line and they go towards that line. This phase plane diagram shows me what's going on, even if I don't actually have the solution yet. Those two lines are asymptotes for all of my solution curves. Now, both of these lines had different behavior. On the line, y equals 5/3 x, we were going out. And along the line, y equals minus x, we were coming in. So we were going out on this line and in on this line. I need to go back to Calc 3 for a minute. If I think of standing at 0, 0, I would say, oh, if I go in this direction, I want to get bigger. And if I go in this direction, I want to get smaller. What if I actually drew a surface that did that? In this direction, it's going up. And in this direction, it's going down. What's that look like in 3D? Say again? Well, a slope is just the direction, right? I'm thinking about like surfaces in chapter 12 in the Calc 3 textbook. And then we had in chapter 14, we had maximums and minimums. We had all these pictures, right? If I'm going up in one direction and down in another, what's that look like? Hold your hand out in front of you. Flat, thumb up, fingers pointed up. Look at your thumb. If you walk from your thumb to your fingertips, aren't you making an upward curve? Now, go from your palm to the back of your hand. Aren't you making a downward curve? Legs go down, saddle comes up underneath me. What we've just described in our phase plane is called a saddle point. 0, 0 has stuff that goes up and stuff that goes down, stuff that gets small and stuff that gets big. Why? Because the 6 and the 2 had different signs. There's a positive 6 and a negative 2. And so our behavior was different when we got t being big versus t being small. Positive infinity and negative infinity. So, what if both of my numbers were positive? I'd still get 2 vectors, wouldn't I? But if both eigenvalues are positive, then no matter which direction we're going, as t gets bigger, we're getting bigger. And as t gets negative, we're getting smaller and smaller, smaller and smaller. So if we think of t as time, then as time goes on, what happens to all of my arrows? They go away from the origin. All of my arrows should point away, as opposed to in the picture we were just looking at, where some of the arrows pointed in towards the origin and some of them pointed out. If I have two eigenvalues and they're both positive, all the arrows point out, which means everything's going away. We call that a repeller. Or a repelling point. What happens if they're both negative? They all point inward. If both numbers are negative, then the infinities and the zeros switch places here. As t goes to bigger and bigger, our numbers get smaller and smaller. Where are my face portrait pictures? I took them out of this edition of the book. I apologize. I don't have pictures in here to show you. I'll have to remember to bring my other book. Either one set of arrows points out, one set of arrows points in. They both point out or they both point in. That's what tells me what's going on at 0. Why is 0 the important point? Well, because if both x1 and x2 are 0, remember what our equations looked like. If both x1 and x2 are 0, we're not going anywhere. 0 stays put. It's a fixed point of this behavior. As time goes on, all of these things are moving except 0. 0 is a stationary point. Go back to Calc 3. When we did the second derivative test, we found these points where the first root of 0, the critical points for fx and fy. We had to do it in 2 dimensions, right? We called them stationary points, not just critical points, for the same bloody reason. I can do this in 3D too. The pictures are a lot uglier. And now I have 3 sets of arrows. And the same thing could happen. I could have 1 set of arrows that point out and 2 that point in. Because I'll get 3 different numbers. Because I'll have a cubic equation instead of a quadratic equation. As long as my numbers are all different. This is the sort of stuff that happens. I've run myself up against the clock. Example 2, page 358, does a 3x3 example. You should read through that one. We will do more of this on Monday. I will see you all. You came in late. I have your homework. Please come get it.